Hello, my name is Jose Rodriguez and I'd like to welcome you to my shop. Today we will be taking a very close and detailed look at the 7x10 Asian's variable speed mini lathe. This tool has been discussed quite a lot recently, whether it is a capable in quality as well as accurate tool. And the purpose of this videotape is to take you through a complete tour and machining demonstration using this very same lathe everyone has been talking about recently, and see how well a performer it really is. I have done only a very few modifications to it, basically just to improve certain functions, and we will be going through those close up and in very uh, close up detail. Then I will be once we look at that, we will be looking at all the accessories that I have managed to make for it, mainly because there isn't too much available at this time, except maybe some commercially available 3 Morse taper and 2 Morse taper attachments that can be inserted into the headstock bore as well as a tailstock bore. But there isn't much in the way of boring tool holder or other types of tool holders, milling capabilities or anything like that. I have managed to adapt various pieces of equipment from the TEG micro lathe to work on this particular lathe, and we will look at all of that very closely as we go along through the tape. Second half of the tape will involve a complete demonstration of its machining capabilities, including milling and threading and so on. We will also do a bit of internal threading, as well as just about anything that I can think of that can be done on this particular lathe, as there isn't too much that cannot really be done. I have made a multitude of projects on it, and some of them in conjunction with a small milling machine that I have also made from scratch, that I will show you at the very end of the tape. So without any further ado, let's go ahead and jump right into the operational part and demonstration of the 7x10 Asian made variable speed mini lathe. Okay, we're going to begin the tour at the most important part of the lathe, and that's of course the headstock. And as you can see, it comes equipped with a nice 3-jaw chuck, and this particular one is a Japanese make. It comes with both inside and outside hardened jaws, which come pretty handy. They are numbered so they can be replaced in the correct configuration, since this is a scroll type chuck. We'll take a closer look at the chuck a little later. Let's go ahead and move to the left. That is the top plate of the control board, the control box, and it's pretty well beat up, as I've had mine for, like I said, for nearly 4 years. I have used and abused this little puppy and still keeps on ticking. Basically, the way it works, it has a speed control knob, which gives speeds from a low end of 400 to about 2900. Mine is the older model. The newer model has a 2-speed gearbox located in the rear of the headstock, which give you a low speed range of about 200 to about 1500 or something like that, and then a high of 400 to 2900. There is a way to slow down the low end of the speed, and I have slowed mine down to about 60 to 80 RPM, something like that. I really haven't measured it, but that does give me the ability to cut the larger size threads without any problem with the carriage running away from me. Those of you who have the 2-speed lever will be able to slow this tool down to approximately 30 to 40 RPM with plenty of torque to boot. On the center, I have the on and off button that I had to replace. That normally operates the main power, and next to it is a center off reverse and forward type switch. We are looking at the gearbox end of the headstock. There you can see the threading chart, one that gives you the correct gear positions as well as number of teeth to use for the specific pitch you are trying to cut. And as you can see, it cuts from 12 to 52 threads per inch. These are imperial thread sizes. Now, there is one individual on the internet who has a web page where he shows you how to cut metric threads with the same gears that this lathe comes equipped with. That is the lever that actuates the carriage feed, automatic carriage feed. It has both forward and reverse, in other words, from the tailstock to the headstock and back to the tailstock. The motor also has a reversible feature, so this gives you many combinations that you can achieve. Sort of I like to sometimes cut off my work with a rear mounted tool post, and that requires a reverse rotation of the motor. This will also allow you to cut a left-handed thread, which is the kind of thread you would need if you were ever to make a lead screw for any piece of equipment. Here we're looking at the cross slide, carriage, and compound slide arrangement. There's the carriage, and that acts on a crank type geared mechanism on a rack. There's the lead screw and carriage rack. The lead screw is a 16 pitch screw. As you can see, the bed is a standard V-type design, which most Asian made lathes seem to adopt. Here you should be able to see the underside of the cross slide, including the 3 jib screws, as well as the compound. I have replaced the smaller metric screws and replaced them with 1032 larger cap screws. Makes it easier to operate and adjust those jib screws. As you can see, the tool holder is a typical 4-tool lantern type holder. A lot of people hate these, especially if they've used some of those fancy holders that use the basically they're referred to as quick change holders. These are a little bit more antiquated style. I have no problem with that, as I'm the type of guy that doesn't mind being inconvenienced a little bit. Here is the locking lever for the half nuts. Here is the threading dial. Here's a tailstock, and it has a 2 Morse taper bore. The problem is it doesn't accept regular length arbors. You need to literally cut off the tang and somehow grind it nice and smooth in order for it to fit. Here's the live center removed from the tailstock. All you have to do is back it up and it automatically pops it off. But you can see how short that shank is. Most other commercially available tooling will be about 1 inch longer. Here's a pretty useful little modification that I did on my lathe. I added a handle and a couple of plastic balls to the ends, and I use this basically by disconnecting the gear drive and then locking the half nuts. I can operate the carriage by hand, sort of like a some of the other model makers' lathes have. This allows me to measure quite accurately my carriage advance, especially when I'm utilizing it for milling jobs. Now I want to discuss a little bit about the tailstock lateral adjustment. This has got to be the most inconvenient adjustable tailstock ever invented. I don't know what these people were thinking. The screw is literally underneath it. You have to loosen it, and then you move the upper portion along this little V or way, square way here. And when you have set it to the whatever setting you wish to have it, you have to remove the tailstock again and lock that screw tight. This little set screw right here keeps the body aligned against the side of that slot there. It's pretty crazy. What I have done is I set mine to within a few tenths of a thousand accuracy and crazy glue the hell out of it. I'll never be able to shift it laterally, but that's really not my wish, as I hardly ever turn any long tapers. At least now I'll be able to routinely mount work between centers and be assured that whatever cylindrical parts I turn, they will be almost perfectly parallel. I was having problems with the tailstock sometimes shifting out of alignment, but now it's literally glued in one position and one position only. It actually, once loosened right there with a central nut, it actually does travel along the bed quite smoothly. I'm not too unhappy about that aspect of it. Okay, let me go ahead and demonstrate some of the motions or movements on this tool. As you can see, carriage is advanced by hand in this manner. I don't very much like these plastic handles, and there's quite a bit of backlash on the gearbox. There's a triple gear box located right behind this casing. Half nuts lock in position like so, and once that happens, the gearbox basically cannot move the carriage anymore. There is no such thing as a carriage lock. It could be built. I've known people who have successfully done that. They have also built a carriage stop system. That's something that I have not done yet, but it's a simple little project to do that will enable the carriage to be stopped at the same position every single time, especially when doing boring jobs and that sort of thing. The cross-light travel is extremely smooth, at least mine is. It does have quite a bit of backlash though, and I have not figured out a way of removing that. It has over 10 thousandths backlash, but so far that really hasn't prevented any problems during normal operations. So you know, but this is a typical problem with these Asian tools. My compound, on the other hand, has a lot less backlash than the cross-light for some reason. Maybe the nut through which the lead screw passes is a little tighter, so that's hardly any backlash. In order to change the position of the compound, you have to literally screw it all the way back like so, and on the surface of the compound body are located two screws, which you then loosen. You rotate to whatever angle you desire, and again we have no way of measuring these angles, as there isn't a protractor to speak of. One particular model that an importer used to have did come with a protractor, but I haven't seen that one since about a year ago. What I have done is actually scribed very carefully some marks that equate to several angles, such as 29 degrees for turning threads and that sort of thing. I like to keep it at a nice shallow angle to the axis of the lathe, so that it basically enables me to remove very minute amounts of metal as I am turning something to diameter. By feeding the compound at a very shallow angle such as this, for every thousandths that you advance, it literally moves the tool into the work about 1/10 of that, or at least a lot less than the dial actually indicates. The dials on these lathes, as well as many other Asian tools, are a close approximation to an imperial, say, pitch. This is a 25, I don't know what they call it. It's, in other words, an inch of travel has about 25 in some small fraction millimeters. Therefore, the dial can be calibrated to somewhat like 40 thousandths of an inch per full turn. It's not really close to that. I mean, what you actually get is something in the neighborhood of like a couple of thousandths more every time you advance 60 thousandths. In other words, every time you advance 60 thousandths, it's really about 62 thousandths. So that's quite an error. But I don't rely too much on these dials. I use a lot of dial indicators as I am performing my various operations. These are only to be used as approximations of actual advance. And that's the way, in fact, everything that comes out of the Orient, unless the importer specifically asks for imperial threads on the dials, I mean the lead screws, which is not something that's that difficult to do. I'm sure they have the capability to do so. They just will not if if the importer does not ask. It's a crazy thing. Okay, let me go ahead and give you a good look at what the gearbox or gear train area looks like. Don't expect to see the gear train of a Myford Super 7 or anything like that. Those are Rolls Royces. These are more like Pintos. The white material that you see on the gears is white lithium grease, which I find is a very helpful additive to the gears. As you can see, my spindle is disengaged from the carriage advance. By pulling this lever out and either engaging it on the up position or down position, you determine the direction into which this carriage will move. So let's go ahead and pull it out and bring it up. It's a two-handed operation. It's not very easy to pull out. It's quite a strong spring on it. And as you can see, the spindle gear is rotating clockwise while I rotate the spindle clockwise as well. Now if I pull it out and bring it all the way to the bottom position and rotate the spindle clockwise again, you'll see that the lead screw gear will turn counterclockwise, and that will move the carriage from headstock toward the tailstock. And the neutral position, of course, is right here in the middle. Now mine also has a neutral position on the spindle, which means it disengages it from the motor drive, which is good when you are performing operations such as tapping by hand using the chuck as a way to either drive the tab, or if you have work held on the cross slide, or with the work held on the chuck itself, it's easier to just rotate the chuck with the drive disengaged. Okay, so now let's go ahead and start off by having the power off. I set the direction and turn it on. And this is rotating at the lowest speed. And as you can see, you can increase the speed in a stepless fashion. Up to 2,900 RPM. Here it is running in reverse. Now the variable speed is just fabulous. This is the thing that sold me on this tool. No matter how Spartan it looks, no matter how, it's like an ugly duckling of the world of lathes, I still didn't care at all, as what I really wanted was a tool that enabled me to have variable speed, which I find just indispensable in most work. For instance, I'm machining something and it happens to chatter a little bit. I immediately, I'm cutting at that speed and I get a little chatter, I immediately come back and slow it down. What I would have to do with a normal machine is stop it, open up the gearbox, change my belt pulley positions. Oh, that's a pain in the neck. Here I just increase it, decrease it, slow it down, whatever. Once you have that, you just won't go back to a regular pulley system. Okay, let's go ahead and engage the gearbox and engage the lathe, and you may be able to hear, or probably not hear, the actual gears. And these are made out of a nylon type material, which is extremely durable. Although I do have a set of all metal gears, these are machine gears that came with the original lathe many years ago. I was able to get one of the last sets that the company was offering. They went strictly to the nylon type gears. Yes, of course these are cheaper to produce, and that's basically at that time when the price started going way down. I know I cringed at the thought of plastic gears originally, but then I realized that when I was in the Army all those years working in photography, all of our processing machines had plastic gears of very similar design. And although chains and sprockets, metal sprockets rusted and gave us quite a bit of problems, these gears never did. So that alleviated some of my fears. And so far, after nearly 4 years of heavy use, I have yet to see any wear on the teeth, or have I ever stripped a tooth on any of the gears, even when doing heavy work. Now I'm going to go ahead and put it on the reverse position, so you'll see it running in reverse just as smoothly as the forward position. Now these are the actual gears that you change when you're going to be performing some threading. By adjusting the ratio of the gears, you achieve the given rate of advance of the carriage to give you a specific thread pitch. Okay, let's go ahead and give you a dry run of how the carriage operates under power feed. Just as simple as that. You engage it and you see the handle turning very slowly, as well as you may be able to see my little tailstock handle also turning. It's as simple as that. You have to agree that it does operate very smoothly. The half nut engagement has to be, because it's such a coarse, such a fine lead screw pitch, 16th. A lot of the lead screws in larger lathes are 8. You have to be located exactly over the threads in order to engage. In other words, you may have to jiggle the carriage a little bit while you engage the carriage half nuts. Here we're taking a close-up of the threading dial as it slowly rotates. You can see it rotating, and you engage it, of course, when the proper number for that particular thread aligns with the index line. It's not that difficult to do. We will be covering that in full detail later on in this videotape and show you that it's really not that difficult at all to do. Once you see me threading, if you had any fears about it, I hope this alleviates them. Now, as I said earlier in the beginning of the tape, I spoke about the chuck being a very good Japanese 3-jaw chuck, scroll type design. But the problem is, what about those instances when you need a 4-jaw chuck? Well, there really isn't one. The company does not make provisions for that type of extra tooling. So you must resort to your own ingenuity to solve that problem, as I have done here. This is the TEG microlathe version of the 4-jaw chuck, and it's a very good one. It is made for the TEG, and therefore it is threaded in the back. Unfortunately, this mount for the 7x10 micro mini lathe is not a threaded mount. Instead, it's a type of a flange that fits in a similarly shaped recess on the back of the chuck. And in order for us to be able to adapt any other type of tooling, we must duplicate that recess, as I have done here. Here we see the female recess that I machined on my TEG microlathe 4-jaw chuck, and that is a perfect ringing fit on that spindle flange. I then also located the 3 stud locations and installed 3 regular hex nuts. In order to install the chuck, you would just loosen the 3 rear nuts, remove them completely actually, pop this out, this slides right out of the recess, insert this one in, and tighten it down with the nuts, because it is a flange that acts as a perfect registering type of system. A thread is good, but unless you have a perfect registering surface, one that self-aligns the unit, because no thread is ever going to be perfectly concentric. You will always have a chuck that runs a little bit off center, whereas a flange, no matter which of the 3 positions I insert this chuck, it will always be centered, at least within a thousandth of an inch in any of the 3 positions, and that I have found to be true. That has been tested by me. Since I have so much 3/4 16 TEG type tooling, I decided to make an adapter that allows me to screw any kind of TEG tooling directly to it, as you can see here. Although this is not by TEG, this is a threaded unit that fits the TEG. It's a catch plate for driving work between centers. Now this unit would replace the chuck itself. This will attach to the flange, the mounting flange. As you can see, here's my female recess in 3 studs. And once that is attached to the back plate of the spindle, I can then screw on or off or whatever, any kind of tooling that I desire. I also made a little 3 Morse tapered threaded spindle accessory. This locks in position with a 3/8/16 drawbar. Whoops, can be having our tooling falling off. Here's a drawbar. This fits behind the spindle like so, and draws the whatever you happen to be using nice and tight inside the spindle bore. Here we have a nice commercially available 3 Morse tapered dead center that fits directly in the spindle and is used whenever you are turning between centers. Here we have a spindle mounted catch plate, just like the smaller one you saw earlier. This one happens to be threaded. This particular one fits our funny spindle just like if it was made in the factory for it. With this clamp I can attach my workpiece, clamp it around it, align it against those 2 V notches, and then it is driven by that little slot. Again with the 3 Morse taper on the center of the spindle to align the work. Now for those instances where you wish to do some boring, you basically remove the tool post like such and insert a homemade boring bar holder as well as cutoff tool holder. When I'm using it for cutoff work, I have it oriented at right angles to the work, and when I'm using it for boring, I have it oriented parallel with the bed. Again, it's just a simple block of aluminum with a slot cut and a hole bored and reamed to accept commercial type little boring tools. These are the types that you can get in sets of 9 very cheaply, although they can be purchased individually, and you can pay as much as you wish depending on the quality. Okay, let me show you how easily the live center is removed. You basically retract it and it automatically pops out. And here is the Morse tapered adapter that I modified. It used to have a long tang back here which interfere with that rod that pops the centers out. So you have to cut it off, and I ground it nice and smooth and even, and it just pops in there just like so, and now you're ready for drilling. When you're ready to remove it, you just retract it all the way, pops right out. So it's actually quite a convenient little method. It's just one that it's a little bit archaic. Most expensive lathes will have actual marks here for allowing you to determine how far the drill has entered the work. I file little 1/8" marks myself. Gives me an approximation of the depth of the hole. One pretty neat bit of tooling that you can make for your tailstock. It's actually something that will take a minimal amount of effort and materials. Basically you would need about a 3-inch square piece of either aluminum plate, say 1/4 inch thick, or even a piece of plexiglass. You would carefully bore a hole along the center point of this little square and insert it into the bore of the ram and glue it either with epoxy or crazy glue, and that would extend about that far out. You would then mount, either attach with epoxy or actually screw it onto the side or top of your tailstock. You would attach one of these little devices, and that would, as you advance, the collar and the ram extends forward. Say you begin with a pressing so that your dial is completely retracted. As you advance forward, this would bear against that little square of plexiglass and give you a direct reading of your advance. In other words, as you're drilling a hole, you would know exactly when you have reached 500 thousandths of an inch in depth, for instance, or whatever measurement you decide your hole needs to be. This is a little attachment that a person who on the internet has quite a nice page featuring this lathe has made, among other things. It's a good little way of measuring exactly when you are drilling. Okay, I think we've done enough talking for now. Let's go ahead and begin demonstrating the operations this lathe is capable of doing. What I have here is a semi-finished part, one of many that I find at my local scrapyard. This seems to have been come from a manufacturing type company who has apparently messed up. Basically, they use CNC lathes and mills, and sometimes the programming doesn't quite translate to the actual dimensions that are required. So when these parts are done wrong, they are usually just simply scrapped. And I pick them up for $2 a pound, and this, you could imagine, could become a pulley already with a shank, a two-step pulley. So we'll go ahead and clamp that onto our chuck. I'll get it centered and nice and flush. Try to rotate it in case there's a little bit of dirt or rough spots. They'll be cleaned off. That way the jaws will tend to grip a lot more evenly. One rule that I try to follow: I don't crank the scroll mechanism too tight. That will harm it. But I do crank all three of them to a relatively tight feel. As you can see, that piece is turning relatively concentric right off the bat. We're going to go ahead and begin our demonstration by just taking a basic turning cut. There will be a cut on the periphery of this first step. At this point, we will assume, for the sake of this demonstration, that this is a raw casting, and we are then to dimension it to whatever dimensions the plan calls for. That will include turning cuts, facing cuts, shoulder cuts, and so on. So let's go ahead and begin. At this point, I'm going to increase the speed a little bit, and I'm going to bring my tool toward the work until it just begins to kiss it. And then by advancing the carriage, I should be able to take my turning cut. So right now I have just kissed the work. As you can see, it's taking a very uneven cut. And that's because the periphery of that workpiece is very uneven. Turning, especially the periphery of objects such as this, will do nothing more than to true them up. It will true them up to perfect roundness. As perfect as mechanical methods permit, of course. Now, since this first pass did not do the job of completely cleaning off that surface, I could either do one of two things. I can advance with my cross slide, or I can advance with the compound. And basically what that entails is turning the dials a given amount, and that will remove twice that amount, because you are removing material from all the way around the periphery. So if I advance 5 thousandths, then I basically remove 10 thousandths worth of material from the total diameter of the workpiece. So we'll go ahead and advance only 2 thousandths, and that should remove about 4, and we will see as we make our cut if that is indeed enough to clean up that surface. And it's removing the vast majority of the material. There's still a nasty little spot there it's just a little bit too deep. It looks like a little gouge or something, possibly on the original part. Now we're just going to assume that as soon as I clean this part up, that will be the correct diameter for it. I leave it up to you to choose what that might be. Okay, now I'm taking these cuts by hand. In other words, advancing the carriage as evenly as possible by turning the crank on the carriage. Once this is done, I'm going to take a close-up of the surface, and then we'll do another pass using the auto feed. And here's the resulting surface. Even with a hand pass, you have to admit it is pretty darn smooth. In fact, there's a fingerprint. Almost like a mirror finish. Okay, let's go ahead and make this cut by engaging the auto feed. I have set the lever behind the headstock for auto feed. I will advance 3 thousandths, and now I have locked my half nuts. We'll increase the speed a little bit, and as you can see, the cutter is advancing toward the left and should make a very nice cut across that surface. Okay. And once again, I'm sure you can see how beautiful that surface is. Usually after a cut has been made across the periphery of a flanged piece such as this, it tends to leave a very sharp burr on those corners. And one easy way of removing those burrs is to do a mild chamfer cut such as this, and that's just simply done by orienting one of the edges of the cutter so that it is presented approximately at 45 degrees to that corner, and you just simply advance and just take off a couple of thousandths, 2 or 3 or 4 thousandths is all you need to do. And that has the ability to render that edge completely safe to human fingers. Same thing is done to the opposite side. Let's go ahead and orient that at a slightly more acute angle. And we do the same thing there as well. Okay, now looking from the vantage point of the tailstock end, we're going to go ahead and begin to dimension these raw surfaces, basically by facing this little flanged end off, and then we will face this one, and then we will turn this one to diameter. This part has an existing hole with an existing thread. We'll go ahead and drill that out. Then we'll set up a small boring bar, perform a boring operation in order to really truly true up that hole. We can do that in either one of two ways. We can either ream it or we can bore it. In this case, we'll go ahead and bore it. Later on, I'll do another turning operation and we'll drill and ream a hole. Either way, it tends to produce very accurate round holes. Twist drill bits are notorious in that they do not produce round holes. It's some other type of geometric shape. It's sort of a microscopic version of it and not something that can be easily discerned, but it is not round by any means. The only way to get a true round hole, one that will accept, say, a shaft of a bearing, is to bore it or ream it. And even that is not a perfect condition, but it only a very, very close approximation. Nothing is ever perfect. Okay, usually when I have an existing hole on an area that I am facing, I like to begin from what will be the center point and draw the tool back toward me. That has a tendency to plane the metal off rather than push it off. As a pushing, in other words, if I'm cutting in this direction, the front point of the tool would be pushing the metal off, whereas if I cut from the center toward me, I am using the side of the tool. You see, I'm going to demonstrate that both ways. I'm going to advance and cut the tool, cut the chip by pushing it toward the center. As you see, the chip is narrow and thin. It produces a slightly rougher finish. Now I'm going to cut toward me. This has a tendency to produce a flatter, wider chip, which produces a more smoother surface. The drawback, of course there's always a drawback to everything, you don't get anything for free, is that because you're using a wider portion of the edge, you have more tendency for chatter, and you need a more rigid machine, one that can handle the heavier forces involved. Okay, now I'm going to turn that spigot to diameter, and again this has a lot of irregularities. You hear that noise? That is chatter. The wide portion of the tool, the left side, began to touch the face. Usually when the tool is not being dragged across the surface and just sitting there, it has a tendency to chatter. The tool needs to be kept moving at all times across the surface that it's cutting. want you to keep your eye on that surface being created. This is no special type of aluminum. This is, in fact, I don't even know what kind of aluminum this is. It was clearly a piece of scrap that was found, and different alloys have different machining characteristics. Some machine extremely well, some do not. This is not too bad at all. I took one single pass, and that's all I needed to clean that up. Very nice. This time I'm going to orient my tool as close as I can get it to the work and still be able to take a chamfer cut. In other words, all I want to do is just take a little shaving off that sharp edge. And that's very nice now. Okay, now the next step would be to remove this, reverse chuck it, and do the opposite sides. Now, these particular jaws will not open wide enough to accept such a large workpiece. We would have to switch over to the other set of jaws, and I will demonstrate how those are changed next. Okay, now the first thing we must do, of course, is remove the workpiece we just got done machining. And now we can proceed with the removal of the jaws. I had this one marked number 3, so I know that this is the number 3 jaw. And that is important because they have to be reoriented in the same order. Now this one popped out first, so we will check the number and see what number that particular jaw is. It should be either number 1 or number 2. And it's number 2, I believe. It's hard to read. So we'll get that one. And here it is. We'll see what this one is actually here. You have to turn them until they disengage. And that's number 3. So this is number 2 and number 3. And you can see that these are outside gripping jaws, whereas these grip either with this surface only, or you can grip piping and tubing from their inside surfaces. Thus they are called inside jaws, and these are outside jaws. Let's go ahead and remove this one. This should be number 1. Yes. Here's number 1. Now they are pretty snug. The fit is quite snug on these. So you have to be sure that you have no traces of dirt or chips or anything like that that will interfere with the fit. Now what I like to do is screw them out until all of them click once, and then bring them in like so until they're fully engaged. Okay, the next step in the procedure, of course, you would protect the outside of the surface you just machined with something like say masking tape or anything like that, and we would place it flush. In this case I'm going to have to use the first step of the jaws, as I cannot open it far enough to allow the second steps to grip that surface. So make sure that it is flat, and I tightened it somewhat, not too tight, and I go around all three positions as I did previously. Okay, we'll go ahead and face off this area first. Throw some light on the subject there. This is quite uneven. That will take a few passes. As you can see, it's taking an intermittent cut. Increase the speed to a more useful RPM. Until we hit the shoulder. I advance the cut into the shoulder a little bit and retract. And as you can see, it's very cleanly and evenly turning that surface that used to be very uneven. And there we are. Once again, it's just a matter of one pass in one direction and then a return pass in the opposite direction, and we've cleaned that up. And just as we did in the previous demonstration, we'll go ahead and take a couple of facing cuts around the end, this surface and this surface. And that should bring all the surfaces except for the long shaft to a true finish. I have just locked the half nuts. Now I'm advancing the tool with my compound into the work. As soon as I begin to kiss it, I can proceed to draw the tool back toward me. There's quite a round fillet, I suppose you can say, on that tool. That part, this portion here is very round, and I have to be able to remove all that material first before I can square it off. These are interesting parts. They're never what you expect them to be, but I like them because they enable me to make lots of bits of tooling that would always require massive amounts of machining. Imagine if I had started with solid stock, how much material I would have to take off or machine off. This is already basically machined for me. I want you to see how nice and slow the spindle runs. That's due to that modification I did to the electronics. It's not something I came up with. It was already suggested to me by a previous owner of one of these machines. In fact, there was a woman who owned one, was using it to make a lot of little decorative bits of brass work for a small boat. Again, reaching that shoulder area. You hear that chatter, and that's because the tool was stationary. Remember, the tool should be cutting all the time. It will cause chatter if you just let it sit there. I have to remove more material in this section here because there's apparently quite a deep gouge on that shoulder. that would be like a rough spot on a casting, say for instance. Hopefully the castings that you buy for engine projects will have enough excess material that you can machine off all of these surface blemishes before you reach or get anywhere close to the critical dimensions. I think this should do it. Okay, now we will do the second face, just as I did on that first smaller face. Now this is quite even. This one is quite even. Now we'll draw the tool back, increase the RPM slightly. Remember that all things being equal, the faster the piece spins, if your feed rate remains the same, you will get a finer finish. Okay, now we will go ahead and set up for a turning cut under power after, of course, I face this end. Almost forgot about that. You should do all of your facing cuts in one single operation, that is one single chucking or mounting. That way they will all be parallel to each other. When you are facing off an area that has no central hole, such as this one, your tool point, that is the edge of the tool that is actually contacting the work, should be at the exact lathe spindle center. If it's below or above, you will end up with a little bump. That is done by either, as you grind the tool more and more, of course the cutting edge will be lowered, and thus the tool needs to then be shimmed up higher in order to bring it back to lathe center. Let's go ahead and set up for turning cut now. Okay, now we have a couple of choices here. We could of course do this by hand or use auto feed. When I'm using auto feed in a situation such as this where I am against a shoulder, I like to cut from headstock to tailstock. That eliminates the possibility of me running smack into that shoulder. So you can see the work is being cut from left to right. It's slightly uneven, and that's being removed. Now this whole piece of work will then be perfectly concentric to all of those cuts. The secret of that is to make all of your cuts in one run. Don't remove this part from the chuck, remount it, and expect these surfaces to be exactly the same plane that they were previously. It just will not happen. This particular chuck, straight out of the box, will give you 2 to 3 thousandths accuracy. Now that's well within even much more expensive 3-jaw chucks. The only way to get true accuracy down to the last tenth is to mount things on a 4-jaw. Then use an indicator to actually read off of the surface of the workpiece. When the indicator then reads 0, that means that you're in 1 revolution. That means that your workpiece has been perfectly centered. if the And here we go, we're almost done. And this should be it, other than chamfering off those edges. We'll be done with this particular part. At this point I can disengage my half nuts, move the carriage out of the way, perform a little housekeeping, remove all of this swarf, and that should be it. Okay, and here we have our finished part. We'll take a closer look at it. So you can see it's beautifully machined on all surfaces. You can see the nearly mirror finish that it contains. Quite a nice job. And as you saw, it was done effortlessly. Of course, if you need to bore that, that's easily done. Now what I will do next is I am going to save this for now. I'm going to switch back to my other jaws, and we'll do a regular turning operation of a length of work. We'll drill and thread one end, and then we will drill, reverse it, drill, and ream the opposite end. So I'll show you two different tailstock operations. Okay, we'll go ahead and proceed with a normal facing off operation as we've previously done. Basically what we want to do is render this areas flat so that we can go ahead and center drill it, and in this case we will ream. The opposite side we will perform the same series of operations, except that one will be threaded. We'll do a little internal threading with a tap. Later on we will do some threading with a die, and then later on as well we'll do threading with the lathe itself. Okay, let's go ahead and try that again. This area was sawn off originally, so it was extremely rough as well as uneven. Those of you who have the ability to saw material, say with a bandsaw or one of those horizontal vertical jobs that you see advertised just about everywhere, will know that usually those cut surfaces are never true. They're always going to be a little bit off as well as rough. And the only way to clean those surfaces off is by facing off on the lathe. Okay, well, I see a little bit of a rough area yet. Take off a little bit heavier amount of material, and that should clean that right up. Notice that every time I make a pass and then I make a return trip across that surface, little whiskers of material seems to still be coming off. That's very typical, especially on small machines. Now there's a little rough area there. I'll go ahead and take that off by turning. You've already seen me do that, so then we'll go ahead and set up for the drilling operations. Okay, I like to go ahead and install the tailstock back onto the bed. That is a simple operation. There's a flange, sort of like a T-flange, that fits across there like so. And as you can see, it slides very smoothly. Then you just lock it in position with this hex nut. Now we're going to go ahead and retract our cross slide out of our way, as we will not be utilizing that at this moment. I've also removed the tool post for clarity so that we can see what we are doing. We'll move this out of the way over here and lock it in position, and make sure that our lead screw is not engaged accidentally. We'll retract the ram, remove the center, and insert our little drill chuck. Now I'd like to take you through the steps that I utilize whenever I drill holes with the tailstock. I always use a center drill. That should become standard operating procedure for everyone. You should never ever attempt to begin to drill a hole directly with the drill bit. That is the main cause of drill wander or hole wander, meaning that the hole will be started not only off center but will be drilled off center, and the more or deeper that you go, the more the drill bit will be flexed in one direction or another. You must first begin by using a center drill. These have a small, very stiff point and then a 60-degree conical area, and these are extremely stiff, so they hardly ever will flex. They will tend to locate center points automatically, and thus enable the drill bit, which is a very flexible tool, to locate its own center also. And once started straight, has no choice but to continue drilling straight. Okay, first thing we do is to unlock the tailstock, draw the tailstock toward the work until it is about, let me make sure my ram is drawn all the way back. You want to have it situated beginning point with the ram as far in as it'll go, just before it starts to pop off that drill chuck. Remember, there's an automatic little plunger that removes any tooling from the ram. We snug up the ram travel, start the lathe, and very slowly advance. I like to begin my center drill holes relatively high RPM, and the first thing I do is I let it touch, and that little tiny point cuts a tiny little dimple, which then locates it. If I try to plunge it in very roughly or fast, there's a tendency that this ram, because it travels in a bored hole, but it has a certain degree of play, a couple of thous, it could deflect. And by allowing the drill point to just barely touch the work, in other words, I've only advanced it a few thousandths, it finds that center point location without deflecting at all. Once it has done so, it cannot deflect anymore. It is automatically seated and centered. Now when I begin to cut with a conical portion, I like to slow down a little bit and prevent any chatter. Let me go ahead and zoom in on that, and you'll see what I am talking about. Once I have reached that point, I like to stop the advance and let my cutter continue cutting. Remember, there's always flexion in any kind of tool. So at this point, it has ceased to cut. So I know that I has removed as much material as it's ever going to remove, and that should give me a perfectly centered hole, or starting hole I should say. I want to go ahead and clean all that swarf off of there, and you should be able to see a very clean hole. There's a little chip inside there yet, but I'll brush that off. There we go. Okay, the next step is to remove the center drill and replace it with a twist drill. And because this is going to be a reamed hole, I have chosen a twist drill that is about 10/1000ths of an inch smaller than the final diameter, which in this case will just be 1/4 of an inch, or 250 thousandths. So here we have a hole that will be drilled out to 240 thousandths of an inch, which will put us just a few thous from the final diameter, and that will be then removed by the reamer. Now whenever I am drilling, I like to use a little bit of cutting oil, especially on aluminum. Aluminum tends to be a bit gummy, especially when drilling. This not only helps to lubricate, but it helps to keep the tool nice and cool. And aluminum tends to sometimes weld itself to the cutting edges of tools. Now, just as I did earlier, I carefully advanced the drill point into the center drill hole of this workpiece, and you should see absolutely no deflection on that tool bit. The drill bit will not deflect. It has no choice. It has to find its center. And we simply continue advancing. Now that it has began to cut very well, continue advancing until we have reached an arbitrary distance of, say, 1/2 inch or so. And after that, we will replace it with the reamer and proceed to finish that hole to an exact 250 thousandths. Ream holes will be, within a few tenths of the stated diameter. That is, if you do the reaming correctly. And reamers come in many types. The ones that we use on the lathe, since they are going to be attached by a drill chuck, are called chuck-in reamers. You have hand reamers. Those are held on a special handle. They usually have a square end to their shank. These are just straight round shanks, which are to be held on a regular drill chuck or a collet. Our drill bit here that I am using is a surplus cobalt steel 240 thousandths bit, as I mentioned earlier. I got this from a surplus house in packs of 10 assorted drill bits. You never know what you're going to get, but sometimes you really make out quite well. Usually they are sold as reconditioned bits. In other words, they have been resharpened. Many times you get what looks like pristine brand new bits though. So many of these, if you were to buy them from a major supply house, you would pay what you would pay for the pack of 10 per single bit. So it's always nice to search these types of businesses out that sell this type of surplus tooling. I have heard out in California there's supposed to be some big aerospace company, I think it's Lockheed or one of those companies, who has a surplus tooling place. You buy tools by the pound. That would be like a candy shop. Now anytime I want to perform any reaming operations on a hole like this, I like to chamfer the edges a little bit. And for that I use a commercial countersink, which I mounted onto a homemade handle that I turned on my woodworking lathe. And it works quite well. It's simply held by hand against the hole, and it just creates a slight chamfer that allows the reamer to enter a lot cleaner into that hole. If it was left square, it would have a tendency to bounce around a little bit. Now, this is a conventional chucking reamer, one that I removed about half of the shank because it was a little bit too long, and this is what I use. As you can see, the flutes are straight, the edges are chamfered a little bit, the cutting edges where it begins to enter the work are chamfered, but not enough to really compensate for a square portion of the hole. It has to be countersunk a little bit. So you can see I have mounted my 1/4" reamer to the chuck, and now I can proceed just as I did with the drill operation, bringing the unit against the chuck that has the work attached to it, lock it in position. And for this operation, or any reaming operation, you want to use approximately half the rotational speed or spindle speed that was utilized during the drilling. That's usually standard, again, operation for this type of procedure. You also want to use a nice large amount of lubricant anytime you ream. That will determine how smooth that job is going to be inside. Since the chips are basically trapped in those flutes, these are not helical flutes that tend to draw the chips out of the hole. They will be trapped, and this is a dead-end hole as well. So you must use a lot of lubricant, very even, slow RPM, and as even a feed on the drill carriage or drill ram in and out of that hole. If you hesitate anywhere along that reaming operation, you will more than likely create a small ridge inside the bore. So you must be careful when you do that. It's not as hard as it sounds. I'm applying a nice liberal amount of cutting fluid to the flutes of the reamer, and now I'll advance into the cut. You see the little chips coming out. And you'll notice that I am cutting at a much slower speed than I drilled the hole in the beginning. As soon as I bottom out, I will begin to retract the tool. Right there. And just as evenly as I went in, I bring it back out. That will ensure the smoothest walls on that particular hole. Now this type of operation will be used on members that will be accepting a 1/4" shaft of some sort. Say if I was making a set of bearings, I would go ahead and ream, drill and ream deep enough, and then part off discs that would become bearings. That way I would ensure that both of the discs, say if I get 2 bearings out of this length of material, they would all be drilled and reamed exactly on center, so they would actually match. If I did them separately, there's a possibility they may be off a thousandth or 2 off center from each other. Now this particular reamer is a 250 thousandths of an inch reamer, and if I would use that if I was reaming a hole that would be a running fit against a shaft that would be, say, just under 250, maybe by half a thou. If I was to insert a pin in it that I wanted to be a say a press fit, I could purchase a reamer that would be 249.5 thousandths, and that would accept a dowel pin of 250 thousandths of an inch as a press fit. Otherwise, you could also use a reamer that's a half a thousandths larger than 250 and have a shank or shaft made out of 250 thousandths of an inch drill rod, and that would directly allow that drill rod shank to run in that bore as a running fit, as a crankshaft on an engine would have to run. And now that we have finished our nice 1/4 inch reamed hole, I want to show you what kind of fit that hole provides. I'm going to go ahead and get me a 1/4 inch piece of drill rod. Actually, it'll be a piece of actual drill, and we'll see how well that fits. I have here a regular 1/4 inch twist drill. I'm going to go ahead and insert it into that hole. And now I'm going to run the lathe, and you should be able to detect almost zero run out on that bit. It's actually quite easy to detect any, even a very minute degree of misalignment or out of concentricity, as even if it was just off a thou, it would actually wobble a total of 2 thousandths, and you would be able to easily detect that even without an indicator. But as you can see, this is running perfectly true thanks to that very accurately drilled ream hole. Okay, let's get ready for the next operation, in which we will proceed by rechucking this piece by the freshly machined surface. I'm going to turn face and center drill this end here. You have seen me do that in the past, so I will not bore you with that aspect of it. Basically, what we will do is we're going to drill a number 21 hole and proceed with a threading operation, cutting a 1032 thread. We will be using a tap, of course, for that operation. Okay, we'll begin this next operation basically by first center drilling our location for the hole that will be ultimately tapped. I turned this, but I did not make any attempt to turn it to diameter. This is actually a little bit larger than this other end. If this had been a real job, I would of course have tried to match it to diameters as closely as possible. I'm utilizing a smaller center drill than the previous one, seeing that this is a much smaller hole that we will be drilling, and you have to match the diameter of the center drill as close to the diameter of the hole you will be using, the drill bit you will be using for the hole, I should say. You don't want to use a number 3 if you're only going to drill a number 21 hole, as we're doing here. Now this is a number 2 center drill, one that is plenty large for the job we are about to do. And just as before, we will increase the speed a little bit, snug up the ram travel, allow that point of that bit to cut that first little dimple, and then slowly but evenly advance it into the work. And all we want in this case is to allow the conical portion of the drill to begin cutting. That's what will allow the drill bit to seat itself perfectly. The straight shank portion of the point is just there to allow the drill bit to begin that center hole. The conical portion is what actually does the job. Now, center drilling is also used at both ends of a piece of work whenever it's going to be hung between centers and turned in that manner. That 60-degree angle to that point is not by coincidence. It matches the 60-degree angle of most live centers, if not all of them, as well as the dead centers that are used. Okay, let's go ahead and this is the number 21 drill bit. As you can see, a lot smaller. This is the correct diameter for any 1032 thread you wish to cut with a tap. And as we did before, make sure that we have a good liberal amount of oil. And we begin to very carefully bring that drill bit until it's just beginning to graze against that conical portion, and you see the little chip coming out, and you see that it is not deflecting in any way, shape, or form. Now, once we know that the bit is well seated in that hole, then we can increase the speed to a more respectable RPM for this diameter and proceed to cut at a slightly faster rate. I'm going to cut until I have broken into the opposite hole that we reamed. And that will take about maybe 3/4 of an inch to an inch. As you begin to get within about 1/2 inch depth, you need to be careful that you do not begin to pack the chips that are being created in those flutes. Those chips need to be constantly escaping through the flutes. Otherwise, you need to get them out of that hole. You can imagine if the chips are not allowed to come out, they will just pack and create a lot of friction and heat, which will then literally ruin your cutting tools, as well as your drill bits. Even though aluminum is a very soft material compared to, say, steel, you still need to make sure that they are kept cool and lubricated. They will surely go dull just as fast as if they were cutting the hardest of steels, if you do not take care of them. You saw how tightly packed those chips were on those flutes just now as I retracted it. Okay, we've now broken through the existing hole. Before I begin to do the tapping operation, what I will do is I will countersink that hole slightly, as I did for the reaming operation. Except this time it'll be a little bit more pronounced. I'll do the countersinking a little deeper this time. We'll again use our trusty little homemade countersink holder in countersink at the lowest speed, and we'll center it by eye. That's all it needs to be, and press against the work until you have created enough of a chamfer that will allow that reamer to enter cleanly. Okay, I think you ought to be able to see very clearly the resulting chamfer in that little hole. Now, most of us think of a tapping operation as something done with a tap attached to a handheld handle, and that's usually the case for many operations that are done outside the lathe. But when you have a lathe, you might as well use the built-in accuracy that the lathe provides, that is, the ability to hold things centered to the rotating axis. That way you can ensure, pretty much, depending how careful you are, you still have to be careful with things that you do, but it will ensure that these threads will be started very straight and true. Now what I like to do in this case is loosen my tailstock so that the tailstock can advance freely across the bed, like so, but not have it so loose that it can actually bounce in this manner. So I want it snug so that it does not bounce, but yet it can actually slide. So I'll slide it forward until it is touching the metal that I'm going to tap, and while keeping pressure toward the work, I rotate the chuck by hand, and I notice that it's beginning to cut a thread, so I retract it about half a turn, and that tends to break the chip that is being created during the cut. It's simply that easy. Now, of course, and I forgot to add a good amount of cutting oil, especially for a tapping operation. You have to remember there are many little cutting teeth performing the threading operation here, and they need to be lubricated as well as you possibly can. The chips that are being created are much smaller excuse me, and so therefore they have to be carried away from the freshly cut thread. Now this particular tap that I am using is a ground tap. That means that the threads on the cutter itself were ground rather than cut. Most of your cheaper carbon steel taps have been cut, and they do produce a slightly rougher thread. This is a surplus high-speed steel ground tap that I found at yet another one of these gas and steam shows that I go to. These are tremendous places for the hobbyist to find cheap tooling. Tap like this would sell for maybe $8 to $10 from an industrial supply house. I think I didn't pay more than maybe $1 for it, if that much. It allows this particular thread size and pitch to be cut with very little pressure. In fact, I can probably get away with using power. I like to keep it by hand because I can control the operation a lot better, and I can see if the thread is being started a little bit off center. Unlike a power cut that happens so fast before you realize something is not being cut straight, it's already cut. So that's why I like doing it this way. Once I reach the bottom of my cut, I can always retract it under power because this lathe has a reversing feature. So rather than have me rotate that chuck backwards 40 times, I can simply throw it in reverse and turn it on, and away it goes. It will actually retract the tap and push the tailstock right out of the way. Once we are done, I'll see my chuck got a little loose there, so what I will do is run it under power and reseat it on that ram. What happened there is I reached a portion of that cutting operation where it was just a little bit too much pressure, and it caused the chuck arbor to rotate. Let's go ahead and remove those chips. We don't want them to interfere as we enter that hole once again. I will use power, this time since I know that I am running perfectly straight. And we may be able to finish cutting that hole under power. Yes, we have now entered the other hole. I felt it go, engage, and under tension it cut about the last 3 threads, and then it went in freely, so I knew that it had reached the opposite end of that hole that we had just reamed on the opposite side. Now I'll go ahead and vacuum out the chips, and we will take a 1032 screw and insert it in that newly formed thread and see how concentric that little baby runs. Oh, I almost forgot, and since I did show you that little T-handle for the tap, normally you could basically start the tap for the first 5 or 6 threads and then unlock it from the chuck, and say for instance it has entered this far in. You could conceivably remove it from the chuck, that way it's left dangling like that, and utilize one of these little tapping wrenches and perform the job with a tap handle, guiding it against that center drill hole with a center from the tailstock. And you would turn it either holding the handle by hand like that and rotating the chuck, or rotating the handle and keeping the chuck stationary like so. I still prefer to use the tailstock held tap, as it does provide a much more accurate way of holding the tap and guiding it into the hole. Okay, we'll go ahead and insert this little 1032 screw. It's a 1-inch screw. As you can see, I'm doing that with just finger pressure. Eventually I think it gets a little bit tight and we need to use a wrench to help torque it in there, like so. That can actually be driven by power until it's almost seated. Now imagine that this would be holding some sort of wheel, and or a little pulley or whatever, a gear. You would have a washer behind the cap screw head, and that would be the job. That would be a perfect job. The wheel, gear, or pulley would be held perfectly concentric against this freshly machined and faced end surface. It would have no choice but to run perfectly straight. Now you see that the head is wobbling on this screw. It's actually the head that is out of concentricity. That happens a lot with these cap screws. I'm going to give you a shot of the screw body and you will see that that's running straight. And here you see that the actual threaded portion is running true, but this head is slightly off center, and that's the way these cheap, relatively cheap screws are usually cast. For the next series of small cuts that I will be taking, I'm going to demonstrate how to cut a very sharp angle chamfer, more like a 45 to 40 degree chamfer, and then we'll adjust the compound to take a much shallower or taper cut. We will do that rather easily with the compound. What I have done is taken my regular cutting tool, the one that I use for aluminum, and mounted it. Normally I have it mounted on this side. I have mounted it to the opposite side this time. And this I will orient it so that this particular edge which will be actually contacting the work is at an angle that's 20 degrees or so more than the angle of this cross slide the compound it is set at. In other words, if I set it like this, that will be parallel. So I want it about 15 to 20 some degrees beyond this angle that this creates. That creates a clearance, because I'm going to be cutting from the rear of the work, not from the front. If I was cutting from the front, in other words, if I was chamfering that front edge, I would have to have this compound swung toward the back, and I would have to very awkwardly operate the handle from the rear, and more than likely it would interfere actually with the chip guard. So because this lathe has a reverse function, you can easily bore, you can chamfer, and you can taper from the back just by rotating the spindle in reverse. One of the neatest features about this particular lathe is that very thing. So let's go ahead and prepare to make our first chamfer cut. You should be able to see that very clearly as we go along. And as you can see plainly and obviously, we have the spindle running in reverse. I will bring the carriage over so that it's almost touching the end surface, and I will advance it forward so that it is slightly beyond the edge that we're going to chamfer, and then I bring my cutter toward the work with the compound and we'll take off material in that manner. As you can see, I'm taking quite a nice chip right off of there. And there's a beautiful chamfer. Now, to remove slightly more material, normally we would be advancing the cross slide into the work. We will retract the cross slide into the work this time. So we'll come back about 10 thousandths and then come back out. And as you can see, it's doing a beautiful job. One that you really could not do by just using the flat of the tool. That would be too much of a cut, too much stress, and it would chatter like crazy. But as you can see, it did a beautiful job, and it took minimal effort. I have drawn back my compound in order to expose the locking bolts, which I will loosen and rotate it to about, I don't know, I would say that's about 5 degrees. I'm not quite sure. Just any given distance beyond the parallel condition that would be, in other words, beyond this surface here. You would need to use a protractor, which the lathe does not come with. That's one of the unfortunate things about this machine, but one that you can easily work your way around. I don't necessarily require a protractor for a lot of my jobs. And just as I did earlier, I'll try to orient the side of the tool so that it is beyond the direction in which this compound will be traveling by about, again, 5 or so degrees, maybe 10. On the long taper type cuts is not that critical. So at this point you see the tool is going to transverse at a slight angle, and this angle will then be duplicated onto the workpiece. What I like to do in this case is to bring it over to wherever I want the cut to end, which will be there, and lock my carriage in position. Then begin making my cuts by retracting the compound only. It may or may not touch, it just removed the whisker right there. So I know at that point I need to advance into the work a certain amount. And you will see as I retract the tool how material will begin to be removed. And already you can see that the actual angle is a lot shallower than this rather steep one we created there. You should also notice the rather steep clearance angles of this particular tool. This is completely necessary whenever we are cutting materials or anything that's aluminum alloy. You need much steeper cutting edges than, say, for brass, which would nearly be zero, and steel, which would be something a compromise between these two. What we have here are cutting angles for about maybe 20 to 25 degrees. These are called clearances. If you were to try to cut brass using such steep angles, the tool would dig into the work and pull itself into it, causing a huge snag, which would, more than likely ruin your work as well as your day if it didn't pull the work right out of the chuck. Okay, so you can see that produced a very nice finish, a very long and shallow taper. I have gone ahead and removed the regular tool holder, mounted my boring tool / parting tool holder, and we're going to proceed to bore the existing opening on this disc. This is again another one of those scrap parts that I found, and I do not know at this time how true running that inner bore is, but we're going to get it perfect with a boring cut. I will be utilizing a commercial brazed carbide type boring cutter. This is one that cuts on the left side, as most commercial cutters do. It has a 3/8 inch shank which fits inside my block bore, which is reamed, and it is locked in place with these two little set screws right there. Okay, when you orient the tool, you want it to basically present this edge to the inner wall of the work so that it has about maybe 4 to 5 degrees angle. It already has a slight angle ground on it, but you want to accentuate that a little bit, especially on a through bore, one where the tool will pass completely through. Now if you have the situation where the bore is a blind bore, then you would want to make sure that this edge here in the front is situated a little bit beyond. In other words, right now it's situated in this direction. You would want it in that direction. That will still give you, this is less than a 90-degree angle, so that will still give you sufficient clearance on the left side of the tool as well as on the front side of the tool. Okay, if we had tools that could cut on the right side, then I could run the lathe in reverse and make my cuts on the far wall with the spindle, of course, rotating in this direction. But unfortunately, that's not the case, as this particular cutter does not cut on that side, and so I have to run the lathe in the normal direction, but that does not permit me to see what the cutting edge of the tool is actually doing. As you can see, I can only see it entering, but I do not see the actual cut. So that's one of the advantages of homemade tooling, that is, tools that you make yourself. If I was to make a boring cutter, I would make darn sure that it would cut on the right side, and that way I could use it with the lathe running in reverse and be able to see very clearly what the cutter is actually doing. As you can see, the cutter entered the work, cut off some material. It was very intermittent because of the unevenness of that bore. Now I have retracted the cutter toward me, or toward the wall of that bore, a few thousandths more, and drawn it back. Just by hearing it, since I can't really see what's happening, I heard it make a pretty even cut, and then it became intermittent again. That means that that hole may be actually tapered, being narrower at the far side or the inner side of that bore, and a little bit wider on the outside. This procedure would be used when you wish to make a hole a specific diameter, and one that is larger than any reamer you might have in your shop. As you get past the half-inch diameter reamers, they do get very expensive, and so you would prefer to do a boring job if at all possible. Now I'm going to go ahead and switch positions and give you a shot of that very nice board surface. As you can see, that's quite a beautiful and true running surface that would be perfect for a running fit, say for a piston if this was a cylinder, or the shaft of a engine or something. Anything that needs to run perfectly true. Now, one neat thing that you can do with a boring type cutter is that once you have bored that hole and you have then basically determined the direction that that bore runs, in other words, it will run along the axis of the lathe, no matter whether it's mounted slightly off center or not. Once you get done boring that hole, it is guaranteed that it's running with in the direction, say, the bed or the carriage travel, which should be identical to the axis of the spindle if everything is running, if your lathe is accurately set. Now, assuming that this surface here is to be mounted to another component, you would want that surface here to be perfectly perpendicular to the walls of that bore. So at this point you can use the very same boring bar to perform a facing off operation. Okay, I think you can readily see how uneven this surface is running right now. And let's just assume that we just finished boring that central space. We would just draw the tool back using the cross slide toward the edge, like so. As we near the edge, since a larger area is being drawn past the tool, and the larger diameter causes a faster surface feet per minute to be passed, you need to slow down the rotational speed somewhat. If this was a large 3 to 4,000 pound machine, I could get away with using faster RPM because the machine would of course be a lot more rigid. You hear that high-pitched noise? That would not be happening. Of course, this can also be attributed to the fact that the boring tool is a relatively thin shank type tool, and by virtue of the job that it needs to perform, it needs to be extended quite a bit out, and that causes that type of a weakness. Now let me retract the cutter. This surface was so uneven that as it nears the edge, it keeps taking progressively more and more material off. Let's go ahead and even it out in several steps. That should alleviate some of that stress. Let's go ahead and apply a little bit of oil. We don't want that tool to run dry. And already that sounds a little more civilized, somewhat, not much. But you will see at the end what a nice surface this creates. If I was to be making a cylinder that would then mate with an engine block, this is the way I would machine it. I would bore it and then face it with the same tool without changing the position of my crossline. And here you can see how nice that bore and facing job turned out. One very quick way one can determine whether their lathe is rigid enough is to attempt to perform a parting cut. Now here you see a homemade parting cutter. It's about 1/16 of an inch, maybe a little less wide at the tip, and about 3/8 of an inch deep. That means that it can part work that is, up to 5/8 of an inch, but in practice it really is limited to about 1/2 inch diameter work. Now, if you notice that the front end is ground to a very steep angle and the top is left flat in this particular example, this makes it suitable for brass and somewhat suitable for aluminum, although it should be, the top would have to be ground back. Instead of being flat across as you see it, it would have to be ground back slightly. In order for the parting tool to cut properly, it has to be set at exactly the height of the spindle center, and it has to be oriented so that it is perpendicular to the work. Otherwise it may experience binding as you're trying to cut the work, and the worst scenario would be that the cutter binds and breaks as you're trying to cut. Okay, let's assume that I have the need to machine a very small part out of brass, one that if you begin with a tiny piece of brass would be extremely difficult to chuck. In this case you would utilize a large, or I should say a longer piece of stock, and then go through the procedures to machine that part, and then you would need to part it off. That is easily done on a lathe even as small as this, if you follow the precautions that I stated earlier. That is to make sure that this surface is at the lathe center and that the cutting edges are presented, both the right and left cutting edges, in other words the midline of that blade needs to be presented at basically as close to 90 degrees as you possibly can get it. The sides are ground back slightly so that they are thinner in this portion of the blade as they are on the cutting edge. In other words, there's about 10 thousandths of an inch taper toward this rear of the cutter. That way only the front portion of the cutter is actually contacting any metal. Now the secret to parting off, you must chuck your stock securely, get it as close to the chuck as you can. In this case I'm about ½ an inch away, my cutter that is, and you require relatively slow speeds depending on the diameter that you are attempting to cut. I decided to recheck my edge, and I went ahead and very lightly honed it. You want as sharp as possible, that edge. If it's the least bit dull, it is such a heavy cut to begin with that you want to make sure that cutter has the least amount of work to do as it's parting through the material. Now, the trick here is not to stop midway through the cut. You must advance at the rate with which the cutter seems to be cutting, the easiest. You hear what kind of sound the cutter is making, and I can tell it's doing this with no effort whatsoever. And soon you will see the little piece will begin to wobble, and at that point it will just fall right off. That little piece would then be reverse chucked very carefully, either on a collet. There you go, it's wobbling, and there it just fell right out. You'll also see that this little parting tool also leaves a very nice finish even on the opposing stock. And let's go ahead and here's a little piece that was parted off, and you see that beautiful finish it created. It has a little bit of a dimple there that would have to be rechucked, and that would have to be cleaned up. But basically that would finish that part, and you gotta admit that it's a lot easier to machine a part before parting it off the parent stock. Now, a grooving tool such as this, or parting off tool, can be used, as I just said, to create grooves. If you have had the pleasure of seeing a hot air engine operate, you will see that it has a funny looking cylinder that has many cooling fins. These fins have to be cut with a slotting tool, which is similar to a parting tool, except that the end edge is cut at 90 degrees to the axis. This is cut slightly at an angle, more like 15 degrees. And the tool would be plunged into the work a given distance, then retracted, and then advanced a given distance, plunged into the work, and so on, until you have created all of those little grooves. You would use a dial indicator bearing against the carriage to indicate the actual amount of travel between grooves. Here I'm illustrating my method that I use in order to measure carriage travel to the nearest thousandths of an inch. As you saw, on the opposite end, or the cutting end of the carriage, you could imagine that that little parting tool or grooving tool has just made the first cut, and now I need to advance it for the second cut. Now I have my dial situated so the needle is pointing to 0, and I would then advance toward the cutter, say 62 thousandths if my blade is 1/16 of an inch. That would then take care of the blade width, and then I would advance, say, another 100 thousandths, make my second cut. That means that the space between each one of those cuts would be 100 thousandths of an inch. And you would do that over and over and over, each time taking a direct measurement or a direct reading off of your dial indicator. Now these little indicators are only about $20, even less sometimes on sale. The little magnetic holder was about $5, and that basically has a V type hole that holds the shaft of your indicator and very securely attaches to the bed, as you can see. It takes quite a bit of effort to remove it. And here you can see the face of the dial indicator, and the needle at this point is on the number 11. So say I wanted to advance the carriage exactly 11 thousandths of an inch, I would move it until the needle was at the 0 position, and that would have advanced the cutting edge 11 thousandths of an inch. And here you should be able to see, I'm going to take you through a small demonstration on how to perform grooves that are about 1/16 of an inch apart. Now remember, this is not a grooving cutter. That would be one that is square-ended. But you get the idea how this would go. If this was a square-ended cutter, that bottom of that groove would be square. Right now I'm sure you're thinking, oh sure, it parted off rather easily through a 3/8 inch diameter piece of brass rod, but how can it possibly cut through a 1 inch diameter piece? Well, here I have a small piece of stock that originally was a bushing that I had made, and I actually did part off several of these from a larger piece of rod. In other words, it was much longer than that. And as I said earlier in the previous reaming demonstration, these created several bushings for me that were all matching. In other words, that whole position was exactly the same on all three of them. Now, for this demonstration, I am using my dedicated parting tool holder. It's a block that holds the commercial parting tool, and I'm going to go ahead and plunge it directly into the work. This is a much wider tool, therefore it introduces a lot more stresses to the actual cut. The cut has to be taken a lot more delicately. And once we break through the center bore, the washer, in this case this will be a washer, will fall right out. If I was doing this on aluminum, I would have to utilize quite a bit of lubricant, as well as if this had been steel. For steel, I like to use a thinner cutter, and one that has the top ground back slightly. This is a flat top cutter. My blade is extended out quite a bit, more than I like to, but since this piece is so narrow in width, I have to hold it pretty close to the chuck. There's very little material sticking beyond the chuck, so I have to, in order for the block to clear the jaws of my lathe chuck, I have to extend the cutter out almost beyond 1 inch, which is far too much. But even though it's extended that far, it's doing a pretty good job. But I notice that it is flexing a little bit as it's cutting. So far I haven't encountered any heavy chatter or anything like that. The secret of parting off is learning how the tool is cutting, learning to feel and to recognize when the tool is cutting well, and then once you figure out what the perfect rate of feed is, you continue that rate of feed. If you stop, let me stop here, you will hear chattering. You must continue feeding, not overfeeding, but you must continue feeding the tool at whatever rate allows the tool to cut well. It's no there is no rule that applies to all situations. It's depending on the material, the lathe, the sharpness of the cutter, the width of it, and of course the operator. Rather than have to buy them and spend a lot of money, you can make these components yourself rather easily and just as accurately as if you had bought them commercially made. And the best part is that they cost pennies in materials. I get all, if not everything, that I have as far as metal stock at a local scrapyard that I'm lucky enough to have in my area. Okay, I have increased the RPM even more as we are getting close to the point where this ring will fall right out. You should be able to see it beginning to wobble, and in a couple of seconds it'll just fall right off. You see the inside bore is beginning to show the cutter. There we go, fell right out. And we clean off the area of the parent material. And we'll dig it up. It's underneath here somewhere. And here it is. I would take that and slightly countersink it with my little countersink. Take that little edge right off. Do the same thing on this side. And this would allow a shaft to pass through and provide nice and accurate support for that shaft. Okay, let's change the subject a few minutes here. I'm going to show you what the electronic control box looks like inside. And I'd like to just give you a very quick rundown of what I did to slow down the low end of the RPM range. Now this is a very simple, archaic little box, as you can see. Nothing fancy here. There is a bit of styrene plastic sort of acting as a protector for keeping chips from going in there. They still do find their way in there, and I could imagine the havoc that those chips could possibly play, causing shorts and all sorts of nasty things. Now at the bottom here you see 4 pots, or what they call potentiometers, and these are oriented. This is the bottom, and if you were looking at the control panel as if when it was installed on the lathe, this would be the far right side, lower right side. We call that number 1, number 2, number 3, and number 4. Now to slow the lathe down, and this is the way I was told to do it, and by the way, this is not a recommended procedure. This is just something that worked for me, and if you decide to do it on your own machine, you do it at your own risk. What I did was to make sure that I did not screw things up as I was doing this. I painted a little dab of color at the 12 o'clock position to allow me to replace the pot screw back where it was in case something went wrong. And what I did was the second screw is rotated slowly counterclockwise, and that slows the speed down. The left, or the number one pot, maintains torque. Now, I'm not an electronic worker. Those of you who are probably know a lot more about this than I. The bottom line is that it did work, and it worked great. So let's go ahead and carefully unscrew the bottom screw and the adjacent one on the right side. Okay, now I have turned on the spindle and I have it set at the lowest speed. Now, in order to prevent any possible shock from my screwdriver tip possibly straying off and touching one of those bare components, I made a teeny little screwdriver out of wood. And now I'm going to go ahead and insert it into that slot and turn it toward the left. And you saw, if you hear the spindle begins to spin faster, then it comes to the slowest possible position and it stops. You want to reach a point where you have an even low speed, but one that is even. And I'll go ahead and situate the camera on the spindle so you can see what's happening. You see the spindle is turning very slowly. If I turn it to the left, it turns rather fast, and that's about the speed it used to be. That's the slowest speed that I used to have. I turn it to the right slightly, reaches a point where it actually stops. And right now it's very rough, although it does have quite a bit of torque. I mean, I'm squeezing pretty tightly, but that's just too slow. This is a perfect speed, whatever this happens to be. And this gives you quite a bit of torque. I cannot stop that. So once we have that adjustment, then as you raise the speed by actuating the knob, you can basically get your complete range of speeds, except the low end is a lot lower than it used to be. Imagine having to thread a 16-pitch screw thread with that chuck spinning at 400 RPM. You know, the carriage will be going a mile a minute across that piece of work. Not what I would call a fun procedure. Now, my lathe is not the newer model, so it does not have the 2-speed lever control that the newer models have. Therefore, if you happen to have one of those newer lathes, you should be able to slow that down to twice or half that speed even. Because remember, this is equivalent to the high speed position on your gearbox. So this should work out even better, and at the same time give you twice the amount of torque at half the speed. During the next 40 minutes or so, we're going to be exploring all of the various milling operations that can be easily accomplished on any lathe, even one as small as this one. We will be utilizing the TEG vertical slide, the one I showed you earlier in the beginning of the tape, mounted to the cross slide, I'm going to take you through the basic alignment procedures, and then we'll begin doing some end mill cuts, side milling cuts, fly cutting, and so on. So let's go ahead and do that next. Okay, the way I set up to do milling on this lathe is using my existing TEG vertical slide, and this sells for about $60. It's one of the best buys in the tool market. I have drilled and threaded 2 matching holes that match the spacing of these holes here, which is 1 inch center to center. Now I like to lower my slide so that it's about 1/4 inch beyond the base of the tool. Make sure there aren't any chips underneath that will interfere with alignment, and I bring that bottom side of that slide flush against the side of my cross slide, and that tends to align it in that direction right off the bat. Then I basically just make sure I'm pressing tightly against the cross slide, and I lock and tighten my 2 cap screws. This one's a little bit difficult to engage as it's quite a deep hole. But anyway, once you get it all locked in position, then you begin to attempt to align the vise. In other words, it has to be aligned in this direction so that this surface of the non-moving jaw is perfectly horizontal to this axis. We can pretty much assume that vertically it is perfectly aligned. At least that's what the factory will guarantee. We just need to make sure that our vise is aligned in that manner so that the bottom jaw or the non-moving jaw is perfectly horizontal. And we'll do that with a little dial indicator very easily. Won't take much. Now, what we do in this case is we bring, as you can see, the needle is moving as I press up, and that's what we will be doing. We will be causing the lower jaw, the non-moving jaw, to compress or lift the stylus until we have, say, a 0 reading. And I'm going to change location so you can see this very clearly as we do this. At this point you see that the needle is not touching the bottom of the jaws yet, so I actuate my vertical slide until I bring the needle to 0, and now as I advance the cross slide, there's very slight, if not 0 movement. This actually jiggled a little bit, and that's probably just a little surface imperfection on my jaw, but basically it didn't move. If it had moved, you would have to, leaving one of the mounting screws tight while you loosen the other one, you would tilt this in either direction until you get that aligned. Now, since I have mine aligned pretty much at this moment, I'm not going to go ahead and misalign it on purpose. You'll have to take my word for it. It's actually very simple to do. And once you get it aligned, you just leave it in that position. You just check it once in a while to make sure nothing has moved. For the next series of milling operations, I'm not going to use my chuck to hold end mills. I'm going to use my end mill holder. It's a homemade 3-Morse tapered unit, and this will give you an opportunity to see what the spindle flange looks like. As you see, I got everything loosened and it literally falls right out. There's not much space back here for your fingers and those 3 nuts. But as you see, the back of the chuck is just like the back of my accessories that I have made. And there you see a close-up of the spindle. This is the male flange, the 3 stud holes, and this is the 2 registering surfaces. This is a number 3 Morse taper bore. Now, using my little homemade 3/8/16 drawbar, I will insert my 3 Morse taper tool and screw it onto the drawbar, and then we'll begin to draw it up tight. Now, my drawbar utilizes a collar that fits inside the inner bore of the spindle, which is 3/4 of an inch. Now it's nice and tightly secure, runs very true and concentric as I machined it right on the spindle. Now, speaking of reamed holes, I want you to see and hear what a good and snug and perfect fitting tool sounds like when you slip it and pop it right out of a reamed hole such as this. Now watch. As I push it in, it gets pushed back out by just air pressure, and when I pull it out, it creates a perfect little vacuum. That's the kind of fit you get that you cannot get with a regular drill bit. Now we'll just go ahead and tighten it along the flat. This is a 1/2 inch diameter 4 fluted end mill with a 3/8 inch shank. That's the way any milling cutter should be held. It should have its own arbor. The problem with mounting it on the regular chuck is that the jaws of the chuck are hardened, and so is the end mill. It's extremely hard. Therefore, what happens is that you have a hard surface against a hard surface, and there's no biting of metal, so that it really doesn't hold at all. It just it can actually slip right out with the forces involved. Now, this type of operation requires that the vertical slide be adjusted rather snugly so that the work does not get pulled down. In other words, the slide could be forced as the size of the tool work against the size of the work. Now, assuming of course that the spindle rotates in this direction, that means I have to feed my work against that rotation, and that would be from the high position toward the low one, never the other way. That's considered climb milling, and that's only reserved for machines that are rigid enough for that kind of cut. Now what we will do is we'll lower it a little bit, and I'll carefully advance the work toward the cutter with my cross slide until I hear it just kissing, and then I will retract it 5 or 10 thousandths, raise it back up, and advance it to 5 or 10 thousandths of an inch beyond that point where it just began to kiss the work. Okay, it has begun to kiss the work, and I am at 16 on my dial, so I will raise it, come back to 16, and advance about 5 more thousandths. Now we lower the work past the cutter. And you see the chips flying off of it. And depending on how crooked or uneven that surface was, that will determine whether we need to do this more than once. Usually it'll take a couple of passes and then with one final finishing pass to finish the job. I retracted the work another 5/1000ths. Increase the speed a little bit more. Remember, if the work is not chattering, you can increase the speed. Use whatever combination of rate of feed and spindle RPM is necessary to give you the smoothest surface without chatter or without any other surface problem. Okay, and that did the job. I'll retract the cutter away from the work and you can see how nice that turned out. Let me put my finger and you can see my reflection of my fingernails directly right on that surface. Very nice. So you can see I attached a little block of aluminum, one that I previously used as I was experimenting with this procedure. I painted the surface with some black marker, and that will give you a immediate view as the material is milled off. This will be done with the end of the mill, and this is basically called end milling. And what we will do is retract the cutter as we need to advance the work against the rotation. Always remember that. I want to raise the workpiece so that this surface that I'm trying to mill is presented to the upper half of the cutter. Since I will not be lowering the cutter at this time, the work, I go ahead and I tighten the slide down so that it will not move down as it's being cut. What I'm going to be doing is advancing in the Y direction that the cross slide provides. Carefully I will advance the work. What I will do is lock my half nuts and advance the work toward the cutter by rotating my carriage crank, the one that's located and attached to the lead screw, and it's kissing the work. Now I retract it, and I would then have a dial indicator positioned the way I showed you earlier against the carriage and actually measure off a given amount. And at this point I just advance the work past the cutter just like that, keeping a slow feed, very even feed, so that the cutter can do the job. We'll go all the way through until the trailing edge of the cutter clears the work, and then we will return it past that surface again. There's always a little bit of material that will be removed on the return stroke. I increase the speed somewhat while keeping the same rate of feed, and that will tend to give me a very, very smooth finish. And you notice the chips that are coming off are very tiny, almost microscopic. In order to create a slot such as the one that I presently have on there, you would just use a narrower diameter cutter, and after making it the first pass, you basically deepen the cut each successive pass until you have cut the slot to the given depth that you require it. I just lowered the cutter, the workpiece, and now I'm proceeding with the pass that takes the material off of the upper portion, the part that we did not get the first pass. I'm removing approximately 20 thousandths of an inch material. At this point, I'm doing quite a nice job of it. Now I'll go ahead and take a close-up shot of the surface so you'll see how nice that turned out. And there you see the surface on the upper and lower sections, beautifully machined and extremely smooth. All with very simple and relatively low cost accessories. Now here I have a commercially available fly cutter. This little unit sells for less than $10, and I have installed a home ground high-speed steel cutter. It's a 5/16 inch square cutter that has been ground for aluminum, that is with high degree of clearance. Okay, let's go ahead and proceed. We're going to be attempting to surface the end of this homemade V-block. Since the fly cutter is a single point type cutter, you need to run it at a much slower speed, spindle speed that is. Also, because it takes such a large diameter swipe, it is equivalent to trying to use a mill that's nearly 2 inches in diameter. You need to run something like this a lot slower than you would, say, a 1/2 inch end mill. Feed rate, again, has to be taken very slowly, and the amount of material that one attempts to remove also has to be a lot less than an end mill can remove. You can hear the cutter making its cut as it passes during each of the revolutions, and as it makes that cut, you should be able to see the rather beautiful surface that it does create. I really do like a fly cut surface. Okay. And here you can see how smooth and even that surface is. This particular V-block was made out of cast material, and it does have, it wasn't a very good quality when I found it to begin with, and it does have quite a lot of microscopic little voids and bubbles in it. But something even that useless, seemingly useless, can be put to good use just by some judicious machining. I now have a pretty darn good little mini V-block that I can use for many milling operations. Well, I think you pretty much get the idea that you can indeed do some successful, although small, milling jobs, meaning that this is limited by its advanced distance. In other words, this slide can only be raised about 1 3/4 inches. The cross slide can only be advanced maybe 3 inches. This is not the equivalent of a milling machine, but for those instances where you need the ability to mill and drill, as a matter of fact, work that is held here can be milled, it can be drilled, it reamed, threaded, the same manner that you would on a milling machine. It's as simple as that. One of the many videotape titles that we have available is one that covers all of the various milling operations that can be done without a milling machine. These will cover operations on this lathe, on the TEG micro lathe, on the TEG micro lathe utilizing an externally mounted drill press, a micro drill press that is, and on a drill press itself. Although it seems rather unbelievable that one could mill on a drill press, it is entirely possible, and my drill press has been modified extensively to allow that type of operations to be done on it easily with great results. Here you just saw me mount this piece of scrap material. Is yet another piece of my scrap pile, out of my scrap pile. I'm going to center drill the ends. You've seen me do this in the past, and then we'll proceed with a turning between centers operation, which will precede the final demonstration, which will be on threading on the lathe. I replaced the chuck with the catch plate, and now I will insert the number 3 dead center, and we'll proceed to mount this piece of work. We'll need to get the clamps that will drive the workpiece. So these are adjusted like so until you have reached an adjustment that will allow the work to pass through it. Like so. We will do the final tightening once we have installed the clamp in position. Now, basically this portion here floats on this slot like so. We place the part that was center drilled into the center hole, and then we bring the tailstock forward until the live center engages the work, and then it's just a matter of applying a little bit of tension and locking everything in place. Now we can just utilize a wrench. Has to be one of the proper size, obviously, to tighten down the clamp. Now the work is driven, supported at either end on 2 center points, and driven by the catch plate which drives the clamp. I decided to man the camera handheld, as this is a difficult shot to get with the camera mounted on the tripod. As you can see, the clamp just about clears the crosslight. I have my cutter as close as I can get it to those rotating clamps, and we will begin to make the cuts. I will be using the auto advance from left to right, as this will provide the best and finest of finishes. Now we'll engage the half nuts and allow the carriage to move across the work. This is the best way to create a almost perfect cylindrical shape. And turning between centers should allow you to flip the work over, and without changing the position of the tool, you should be able to clean off that little area there that will remain unmachined. And it should turn out to be flush with the previous machined section. Now we have reached the end of the cut. I will now reverse the work, and hopefully we will be able to machine the remaining little portion so that it is the same diameter. Here we have reached the point where I left off. This is the portion that was being held, and I have a little bit of a line right there where the two diameters join, but I don't really feel much of a ridge, so here's an uneven area here that was not machined. Let's go ahead and increase it a little bit more. And that's still pretty much taking somewhat of an intermittent cut. But it shows you that you can reverse. I mean, this obviously needs to have more material removed from the diameter in order for it to be turned to a perfect cylinder. Now this little line right there, like I said, I feel no ridge of any sort. So you can see how nice that turned out, basically by just holding it between centers. Probably the most accurate way to mount round material is to use a 4-jaw chuck. This will enable you to center that stock to less than a thousandth, even, and if you're careful, to just a few tenths of a thousand run out. As you can see at this point, I have a huge amount of run out. In fact, let me run the lathe very slowly, and you should be able to see that work rotating up and down, and watch the needle moving wildly from left to right. Now, the idea here, since you have 4 jaws that are individually adjustable, is to find the closest position that gives you the highest amount of deflection of the needle, which in this case is here. So this jaw is basically too high and the bottom jaw is too far in. Therefore the work is being raised a little bit too high. So very quickly what I do is I loosen the bottom jaw and then adjust the upper jaw, and the needle should be moving toward the left a little bit. That should reduce it somewhat. Okay, now we find the next highest position, and just as I did before, loosen the one opposite to that and tighten the other one. Now you see I'm only about 5 to 6 thousandths out. In this point, this particular situation, this is my high point. So these two have to be adjusted individually. So I'll pick one of them at first. We'll take a minor adjustment, and now I'm only about 4 thousandths. And I'll do that with the opposite jaw. And now I'm less about 1,500. So we will find the high position, which is right there, and I'll tighten this jaw down somewhat. And now you can see that I am almost perfect. What you see being measured are imperfections of that workpiece. So it's as simple as that. It just took me a couple of minutes. If I hadn't been explaining it, it would have taken a lot less time to actually do it. And here we go. That's it. Now I can go ahead and turn that to any diameter, create a shoulder, which will ensure me that it will be concentric to this existing surface, because I have set it to within less than 1 thousandths. Okay, this will be the very work piece that I will use in order to turn a 3/4 16 thread, similar to this one right here, except it'll be on brass. We're going to turn this down to the beginning diameter, which will be just under 750 thousandths, actually about 745 thousandths. The actual major diameter of the thread is always a little bit less in practice than the what the nominal size of the thread is named. For instance, like if it's a 3/4 16, it's not really 3/4, it's just a few thousandths under. So we'll take a very light cut, bring it down to about 745. Then we'll leave that alone for now. We'll face, of course, the edge. I will cut a recess, a clearance slot for the thread to the cutter to emerge out of the cut. And once that is done, we'll come back to the gearbox and set the correct combination of gears to give us a 16 pitch. Then we'll proceed with the various operations, and you should be able to follow along very easily. I will also show you an alternative method of not using the little threading dial. For those of you who don't like to use the threading dial or feel a little bit uncomfortable about its use, I'll show you how you do not have to use it at all, especially with this lathe, because of the reversible feature. And we'll get more into that as we begin the actual cutting of the threads. And here we have the freshly prepared surface that will be receiving our 3/4 16 thread. Okay, at this time we're gonna get ready to put the gear train that we need, the combination of gears that we need to cut a 16 pitch thread. As you can see, here's the number 16 indicating the pitch, and it says that on position A I need to put a 40, on B I need to put a 60, C 60, and D 40. What that gives us is really, since the lead screw, it's already a 16 pitch, all we need to do is create a situation that gives us a 1-to-1 ratio, and that's what that provides. Otherwise the gear on position A would differ from position D. So basically we got the same gears on A and D that gives us a 1-to-1 advance rate. So for each revolution of the spindle, the lead screw will also spin 1 revolution. Let's go ahead and remove the cover. You saw me do this earlier. We'll put it aside. And I will remove the lead screw gear first. Oops, don't want that to fall off. This is kind of an awkward system. If you were to pay big bucks for a lathe, you would not have to do this more than likely. You would have maybe a quick change box or something like that. Now, these are the plastic gears, but I do have a set of metal gears from which I will get my second number 60 gear. It's quite a nice little gear set, and it's just too bad they don't offer it anymore. It was a little bit pricey, even from these types of companies at $40-something, but well worth it. So I'll take we're gonna set up the double 60 stack, and really what I wished this had was a just a thick double thickness gear for that position there. This is the metal gear, and I'm sandwiching it with a plastic gear, and we'll go ahead and place that right there for now. The position letter A is the one that drives the spindle once you connect the lever, the feed lever. I may have to connect it just to be able to turn it. Holding onto the spindle. It's kind of a tight fit right now. There we go. This is what kind of kept me from attempting to do any threading when I first got the lathe. It was just such a pain. But, you know, as I said earlier, I've learned not to mind it too much. And there's a little key right there that you could either crazy glue in position. I've done that, but it just keeps coming off. Let's just go ahead and put this aside for a second. And now we're going to loosen this pivot right here, and then we'll loosen this one. Since we are attempting to put gears that may be of different diameters, we need a double adjustment type system that will allow us to adjust the meshing of all of these gears so that there's just minimal but some backlash. You don't want a lot of slop, but then again you don't want it too tight. So we'll loosen this a wee bit, just so that it slides. Just loosen up so it slides. And then we'll go ahead and loosen this one. Just like that. And we will place the number 40 in position D. And the number 40 in position A, as the chart indicated. Then the double 60 in positions B and C. And now we bring everything together like so. This is the way that will be fitted. But first we need to install, of course, our retaining bolts. So as you can see, this is quite an operation you have to undergo anytime you do this. That's why, unless I am turning threads that are, say, smaller than a 1/2 inch 20, I prefer just to use the taps and dies. It's a lot quicker, and if you're careful it's just as accurate sometimes. But for the really super accurate threading, you require to do it on the lathe. That's the best way of making sure that you get the best and highest degree of accuracy. I have to loosen this a wee bit more again, and we're going to bring it up. As you can see, this gear meshes with the rear or the first gear in the stack, then the second gear meshes with the last one. So we're going to go ahead and reach back here. This is where you need to have a couple of extra hands. They don't make it too easy here. And now we tighten this one down here. And we check to make sure there's just a little bit of wiggle. Give it a couple of turns by just turning the chuck, and everything is working. So now we're ready to put the cover back on and begin our threading operation. Okay, and here's one last shot of the gear train operating. I have applied a little bit of the white lithium grease, and we're ready to roll now. Okay, I have set the compound at 29 degrees by using this little gauge right here against the side of the cross slide. I have my 60-degree tool oriented perpendicular to the surface of the work, and that is achieved with a little gauge such as this. It is placed against the side of the work like so, and then the tool point is adjusted by moving the carriage and compound and cross slide, as well as loosening the tool post until it is brought in to a position that is perfectly perpendicular to the work as you can possibly get it. And here you should be able to see very clearly what I mean by that. Notice that the point of the tool is in line with the little gauge, the point on the gauge, and this portion of the gauge is flush against the machined surface of the workpiece. And that's basically all you need to do to get that tool set up, compound set up. Only took me actually about a minute to do that. Okay, now the carriage as well as cross slide and compound travels are performed as such. You bring the point of the tool until it just barely kisses the work, and then you would adjust the dial, in other words loosen the set screw and rotate the dial so that it is set at 0, and then since the tool is kissing the work at this point, you would also loosen this one and set that at 0, and those would be our reference starting points. Now during actual cutting, you would engage the half nuts when the correct number for that particular pitch passes by the indicator on the threading dial. We'll be looking at that and discussing that a little more in detail in a couple of minutes. But at that point, as soon as you engage the half nuts, the carriage will start to make a movement toward the left, in other words toward the headstock, and that would begin to cut the first pass, or the first preliminary thread. Then we would use a threading gauge to check the actual pitch of the thread that was just cut with that first pass, to make sure that it is the correct threads per inch. And I forgot to tell you that as soon as the cutter reaches this clearance point, you disconnect the half nuts. Now this happens at a fairly fast rate, so you have to be very alert. Later on I'll show you a method that does not utilize the threading dial, but at this point we're going to learn the proper way, and that is with the use of the threading dial. Now once the first pass has been made and the tool has made its travel all the way to the clearance point, you disconnect the half nuts, and then the carriage will stop at that point. Then we retract the tool back so that it clears the surface of the work, and then we return the tool to a point beyond where we began, and then move the cross light back to number 0. In other words, we were at 0 to begin with, and we advance the cutter into the work with just a compound. So it goes like this: you advance the cutter with the compound 3 or 4 thousandths, make a pass, stop it, retract it, go back to your starting point, bring it back to 0, and advance with the with the compound once again. So your cross light feed is always kept at 0. Okay, the only advances we're making are with the compound. And because of that, because the compound is set at exactly the same angle as the right edge of the tool, only the left side is actually machining the left side of the thread, and the right side is just following along. The last couple of passes that we will be making, taking off the last couple of thousandths, we will make by plunging the tool directly into the work. That will clean up any irregularities that may exist on the right side of the right wall of the thread, of the V thread. It's not as difficult as it is to explain it. Once you see me do it, you will be amazed at how simple really this is. Okay, let's go through a dry run before we actually begin to do the threading. As you see, I have my cross light dial at 0, as well as my compound dial. Now, at this point, I would advance about 3 thousandths at first. And for a 16 pitch thread, I can use any number along that dial, as long as I always use the same number. In other words, if I use, say, the number 1 coming around now, I engage with the number 1, the carriage is traveling toward the work, and I would then disconnect it, and then I would come over here, retract the cross slide, move the carriage over to the starting position, put the cross light back where it was at number 0 once again, and advance the cutter another 3 thousandths, and then engage once again as the number 1 passes. By doing that, that ensures that the cuts each overlap each other. In other words, they stay synchronous to the previous cuts. Otherwise you would have a horribly crossed, threaded type workpiece, one that would be useless. So that is the reason why we use the threading dial, to ensure that all subsequent cuts, in other words, as many cuts as it takes to produce that thread, will always be synchronous with the previous one. Okay, let's go ahead and begin threading, and hopefully we'll get a nice 3/4 16 thread that will fit one of our little tag accessories. Okay, let's go ahead and begin taking our very first pass. I have advanced my cutter about 4 thousandths, and I'm waiting for the number 1 to pass, and now it has. And as you can see, it's taking an extremely light cut. I reach the recess and I remove or unlock the half nuts, retract the cutter back with the cross slide, return it back to a point beyond the original starting position, and then bring the cutter back to the original starting point, which is the number 0 on your cross slide, and advance another 3/1000 or so with the compound. Now we make a second pass. This is a little bit heavier. And we just repeat the same routine, retracting the cutter, moving the carriage back to the starting position, and setting the cutter back to 0, and advancing it into the work another 3/1000 with the compound. Notice that the last 2 passes, to include this one, is perfectly tracked or synchronous to all the previous cuts. Now let's go ahead and check our freshly machined beginning of the thread with one of these little gauges, and this is the 16 threads per inch gauge right there. And we basically just lay it on the thread and make sure that those little points engage the freshly cut grooves, and indeed they do. So that ensures me that I have set my gears correctly for that particular pitch, and now I can proceed without any fear that I may have set it wrong and I'm producing a thread that is not quite 16 pitch. It can happen. So here we go one more time. This goes relatively quick after a while, once you get, used to the movements and adjustments you need to perform and the sequence in which you have to perform them. What you normally should do is to sort of count in your head the different movements that you have to make. That way you don't mess up. Okay, now I'd like to show you the alternative to this system, and one that you are able to perform with this particular lathe due to the fact that it has that reversing feature for the motor. Now I'm going to go ahead and retract the cutter, bring it back to a point beyond where I began, put it back on 0, advance 2 to 3/1000 with the compound, and then I'm going to wait for the number to pass and engage it. And as you can see, it's traveling across, but when it reaches beyond that slot, I will just simply stop the lathe. Okay, now without disconnecting the half nuts, I will retract the tool so that it clears the surface of the work, throw it in reverse, and that will bring the carriage over to a point beyond the beginning of the thread. Stop it, bring the cutter back to 0, just like we normally do, and advance another 2 or 3/1000 and throw it on forward. And as you can see, it's making the second pass perfectly synchronous to the previous one. Retract the cutter, throw it in reverse, stop it, Move it back to the 0 position on the cross slide. Advance the cutter 2 to 3 thousandths and throw it on forward. And that's all there is to that. It's as simple as you see me do it. Okay, so let me go ahead and I'll continue making these cuts. I don't want to put you through the torture of watching me do this 30 times. So when I am nearly ready to finish the thread, I will be back and then we'll begin to test it against an actual workpiece. Okay, now let's make the last pass. I tested it against the workpiece that I have and it was a little bit tight, so I'm making just a couple of very light passes. In other words, I did not advance the tool at all. I'm just making repeated passes without advancing the tool. That tends to always remove the last little remnant of metal that wasn't removed because of a tool flex and that sort of thing. Okay, that's just taking some dust off of there. Okay, now this thread point is very sharp at this point. And by the way, I was able to judge the thread because I know how deep a 16 pitch thread should be. So by having my compound set at 0 to begin with, I knew when I reached a certain measurement on my compound dial that I had reached the proper depth. Now I'm going to increase the speed a little bit, and I'm going to just very lightly, hardly removing any metal, I'm going to flatten those peaks on those threads, just like that, and barely removing metal. It would also help to chamfer the edges on that thread as well. But let's go ahead and test this little bit of it's a little faceplate, and we'll see how that fits. Let me engage it. Here we go. As you can see, it's a very good, almost wobble-free fit. That's what you are after. You definitely do not want any wobble on these threads that are meant to be holding workpieces that are going to be spun off of that thread. And here you see the little faceplate spinning extremely concentric without even having a registering surface behind the thread, which you normally would have to have. It is being held in this degree of accuracy solely by the thread. That's pretty good. That's pretty good in my book. So I think you'll have to agree that this was a very simple procedure. It took hardly any effort, at least in my part, and it shouldn't take that much more effort even in if you have never done this before. It just takes a little bit of planning and careful thought, and you know, be willing to mess up a couple of pieces of metal, waste a little bit of material until you learn. And once you learn it, it's like riding a bicycle. It just comes natural. Okay, let's go ahead and set up for another form of threading, one that we didn't do up to this point, and that's threading with a die, using a die holder held in a tailstock. Now the idea here is to keep everything locked tight except for the actual tailstock. That can be left loose enough so that it can slide, although very snugly. Let's go ahead and move this out of the way so we can allow that to slide. And the workpiece that we're going to thread is just under 3/16 of an inch in diameter, which is a correct size for a 1032 thread. And what I have done is chamfer the edge somewhat to allow easy entry of the tapered portion of the die. In other words, the part of the die that says face, cut this way. In other words, that's an area that's it's machined at a taper so that it can gradually begin to cut the thread rather than try to cut the full thread bluntly. It's like a tap. Taps have various degrees of taper on their the beginning of the cutting flutes. Okay, so let me bring this forward, and this is strictly a hand-operated type cut. We're going to go ahead and turn the chuck by hand as I push with the tailstock forward. And now I feel tension. That means that I am beginning to cut a thread. And so very carefully, and making sure that everything is straight. In fact, I might want to snug this down just a wee bit, because what I want to do now is basically use my chuck key as leverage and rotate the chuck like a quarter turn and reverse it a quarter turn. Rotate it a quarter turn and reverse it a quarter turn. And that squeaky sound you hear, this is very characteristic of brass. So even though usually we do not put lubricant on brass, I like to use it when I'm tapping or threading. Just keeps that noise down. So you can see already we have began to cut some rather nice little threads on here. Because we are not into production work, this can be done as slowly and as carefully as possible. We want to be able to create the straightest, truest thread possible. And doing it in this manner just about ensures that that's what is going to take place. Okay, so now we've entered the thread once again, and we'll proceed with the rotations of about a quarter turn, and we'll gradually then cut the thread to the depth that we require. As you can hear, the squeaks are now gone. Not that it was doing any harm or causing any problem to that thread, it's just a little bit annoying. It's just something inherent in brass when you're tapping or cutting with a thread, with a die. Now you can also cut this by gripping the chuck, loosening these rear 3 screws, and just rotating this little unit that fits in a shaft that's a slip fit through the bore of this cylindrical unit here. And that's just another method of cutting the same kind of thread. Okay, now that we have cut what appears to be a sufficient length of thread, we can either retract the unit by hand, or since we have a reversing feature, we might as well power it out. And there you have it. Another beautiful threading job. Let me go ahead and get a little nut that will then fit on that thread. And there we are. Another perfect job. Okay, so far you have seen me cut an internal thread with a tap, a simple external thread with a die, as well as threading with the single point method on the lathe. There are other more intricate threading operations that are possible, such as internal threads on a through bore, as well as blind type threading jobs, and then other similar type projects that can be done with a similar tool as an internal threading tool, in which you cut internal grooves for retaining rings on certain bits of work that are going to have a shaft locked inside them. These types of operations are usually considered more advanced, and these are fully covered on another videotape that we offer called Threading on the Lathe. If you're interested, full information on this videotape is on the TEG Microlathe webpage. Now, making all sorts of tooling and items such as that on the lathe is a lot of fun, but the real fun comes when you start building projects that actually do something. And at this point, I'd like to show you very quickly some of the steam engine projects that I have made strictly by using a small lathe like the one I just demonstrated, as well as a small milling machine that I will show you after we get done looking at these little engines. This is the culmination of all of those machining operations and practices that we learned, and this is the final step on applying what we have learned to produce something that actually operates and runs and actually makes me extremely happy to have these little machines. Okay, let me give you a quick example of how these little engines operate. I'm running this one on just about 10 pounds of air, 10 psi, off of a small compressor. These little engines were made entirely from scratch, and basically, except for some of the hardware, nuts and bolts and that sort of thing, were made entirely also out of scrap material. This particular one can be throttled down to quite a slow speed. This kind of slow speed such as this and smooth operating qualities are basically due to the fact that all of the parts, the running parts, are so well fitted that it enables it to run that slow without the impetus that the flywheels normally provide. And here's another little vertical engine. Pretty neat, I'm sure you'll have to agree. And here's another pretty nice little beam type engine, overhead beam, and the piston operates overhead like from the top, as you see there, instead of from the bottom. Very nice. These are just a few of the little engines that I have built, all from scratch, with just minimal amount of time invested and relatively low amount of tooling. You too should be able to create little projects such as these. How's this little puppy for something cute? This is a 1/4 inch bore, 1/4 inch stroke, what I would consider the mother of miniature engines, although I have seen smaller ones. I'm running extremely minimal amount of air in here, as if I did it at a higher pressure, this little thing would probably disintegrate. Okay, so that gives you an idea what you can do after you are tired of building, tooling, and that sort of thing. You got to put the tools to work to produce something useful, such as this. Okay, and here I have what's probably my most extensive project I have ever attempted, and that is to build a fully operating milling machine from scratch, just utilizing some components for the TEG microlathe, as well as a lot of just regular raw materials found at the scrapyard. On the foreground you see a fully operating 60:1 ratio dividing head. That is this little unit here. You see the spindle turning. It operates from a worm and gear located in the back. Here we have a small horizontal rotary table that gives you divisions up to 60, or any number that's equally divisible into 60. But the most important job here is the mill. Took me about 2 months to build it. I fully documented it on a 12-hour videotape that I presently have available for sale, and that will have a news release that will be appearing on the TEG Microlathe webpage in the next week or so. It is a variable speed unit with the ability to drill up to 1/2 inch holes and handle 1/2 inch end mills, as well as fly cutters and anything else that a mill normally would use. I'd like to go ahead and turn it on. I have my drill chuck at this point installed on the spindle. The headstock is basically a TEG microlathe headstock, and a few of the other components are just that, parts of the TEG microlathe, although I did build a dovetail riser block from scratch to increase the spindle center to column swing capacity. The milling table has 9-inch advance on the X direction, 5-inch advance on the Y direction, and stops on both axes. These are located right here. And these operate against the sides. They are locked, and then as the table travels, it will butt against the stop block and give you a perfect way of stopping always at the same exact spot. It has adjustable dials and extremely accurate little table. As you can see, I have complete control of my variable speed from very slow, and that is only about 150 RPM, up to about 450, and that is the lowest speed setting on the pulley. Setting the speeds at different ranges is easy. You just pop the belt off and wind it onto the next step. And that gives you a speed range from about somewhere in the neighborhood of 240 to 720 RPM. Again, fully adjustable with the speed controller. And plenty of torque. That actually starts to burn your finger if you try to stop the chuck. You need to drill a hole with a very small drill bit, one that requires high RPM. That's easy to do. You simply change the speed to the highest position, which is about 5,000. You can start slowly and go to the top speed. And that will ensure that you have the correct RPM for the small drill bits that require it. The larger drill bits, of course, cannot be spun at that type of speed, so then we have the lowest step, which, as I said earlier, was only about 150 to begin with, up to about 450, from 150 to 450. Not too bad. And here's a close-up of the milling vise, which was built from scratch. This was done right on a drill press used as a milling machine. The strap clamps and the slots on those clamps were milled directly on the Minilathe, on the 7x10, using the vertical milling slide from TEG. Here we have the worm gear assembly in the 60-tooth gear. This is what gives the 60-to-1 ratio. In other words, for each full revolution, this main spindle rotates 1/60th of a revolution. That means that for every revolution, you rotate the spindle 6 degrees. Now, if you would notice that my dial is also engraved, and that has engravings from 0 to 60, and then half engravings in between each full engraving, giving a total of 120 engravings. So I can further break down the actual advances. In other words, if I was to advance, say, 10 full divisions, that would advance the spindle the equivalent of 1 degree. If I advance one full division, that advances the spindle 1/10 of a degree, and of course if I advance it half a division, that advances the spindle 1/20th of a degree. Now the dials also float. They are fully adjustable. I have two dials here. One is a divisible into 60, 120 and 60, and then this one is 100 individual divisions. The reason I have that is because sometimes it's easier to figure out something. Say for instance, it'll be one full turn plus 0.09 hundredth of a turn. Well, 0.09 is hard to compute on a 60 division wheel. So what I have done is given myself the ability to be able to break down or to divide a rotation into 100 equal divisions. A couple of examples of how you would utilize the dial with 60 to 120 divisions, as well as use the one with the 100 divisions, would be, for instance, if I was attempting to divide a workpiece into 5 equal divisions, you divide 60 by 5 and you get 12. That means you have to rotate this dial 12 times from 0 to 0. That's 1, 2, and so on until you reach 12. Make your cut and then advance another 12 for your second cut, and so on and so on. Now, say for instance I was cutting a gear with 55 teeth. I divide 60 by 55 and I get 1.09090909. It's kind of an infinite number. So let's just round it off to 1.09. That means it's 1 revolution plus 0.09. In other words, 9/100ths of a revolution. Well, I cannot divide hundredths with this wheel. So I will go 1 full revolution back to 0, and then lining up my hundredths dial onto 0, I would advance until I reach the number 9, which would be, I'm sorry, right there. And that would give me the ability to use decimals, in other words fractions, and factors of 100th of a revolution. Gets a little complicated. There are so many different divisions that are possible. As you could imagine, the simple worm and gear combination gives you a 60 times 60 or 3600 divisions, possible divisions. And here we have the under base of the unit, which is dovetailed, as you can see, and that fits the TEG microlathe bed perfectly. So if I want to do some very fine engraving, say for instance of a 360-degree protractor wheel, I can replace the headstock with this unit and then use my engraving tool to cut my divisions. I would be advancing my dial every 10 divisions, which means 1 degree advance on the spindle. Now this other unit here is a simpler unit, one that allows just some basic divisions of numbers that are divisible into 60. So you can conceivably do 2, 3, 4, 5, 6, and so on, 10, 12, 15, 30, and 60. It accepts any 3/4 16 threaded bit of tooling, such as chucks, flywheels, not flywheels but faceplates, as well as take proprietary TEG collets. The way this operates, there are 2 halves that are linked together and can rotate, and then a tapered plunger plunges into one of the 60 holes that are located on the lower plate, on the periphery of the lower plate. And now that upper plate is fully locked. This of course would be clamped to your milling table. Work held horizontally. You could drill a series of radially spaced holes. You can do milling cuts, say from center out or at a tangent. You can do circular slots, and there's really no end to the types of cuts that you could possibly do on something as simple as this. This was made out of a couple of slabs of aluminum rod that I found at my local scrapyard. Well, we're getting close to the end of our time. I appreciate the time that you spend watching this tape. Is rather long. And I also would like to stress that please give this tool a try. I do not represent this tool though, but it is a darn good little lathe that will allow you to do quite a number of, from the simple to the very intricate type of operations. So again, I'd like to thank you and bid you goodbye until the next time. Bye bye.